Okay, so I think I've got all of the assignments for Unit A and Unit B on Canvas and available. So that's right in the readings for Unit A. There's a reading for Thursday, so both the perusal and the reading exercise is available. There is a Unit A comprehension assessment that is due, I think this upcoming Sunday. The due dates are on Canvas. And then there's also a Unit B comprehension assessment that's due, I think, a week after that. The Unit B one's going to be a little bit different. Most of these unit assignments are going to be auto-graded Canvas assignments. We're going to kind of go through questions that kind of assess the concepts that we talked about during that unit. But for Unit B, we're going to do something that I think it's next week. That what day is today? The 17th. So yeah, I think it is next week. For Tuesday of next week, we're actually we're not going to have class, and I want to have you use that time to do kind of a system scavenger hunt, where you're going to look around ASU's campus for a system, and this is explained in the Unit B comprehension assessment. And you're just going to find the system. You're going to list its variables, following the rules that we'll talk about today. And you're going to draw a causal loop diagram of it. And then basically there'll be a bonus where you'll be able to match it to what's known as the systems archetype, which is something that we're going to learn about on Thursday in a couple of days. And that, I think, because it's going to be the only one that's hand graded, so Canvas on these auto graded things doesn't allow for the concept of bonus credit. For the hand graded ones, you can. So for this hand graded one, I've got one of the items on the rubric is actually bonus points. So it's the only one of these that I plan to have that will have this sort of bonus credit. So, you know, I think there'll be roughly 10 of these. And I think we have a policy of dropping the lowest 5. Like the Unit B one might be one that you might consider not dropping just because it has that, or rather consider doing just because it has that opportunity for bonus. But you can take a look at that on there. If you go to the Unit B assignment on Canvas, I've actually posted a sample of, if I was a student, here's what I would submit to get the full credit on it. So you can see my little 2-page upload of that, of a system that I picked on ASU's campus and how I went through that process to give you an example of what I'm looking for. So administratively, I think that's about it. Are there any questions? Okay, let me see if I can move this over a little bit. All right, so today, wrapping up Unit A. So this is, I guess it's the 17th today, if I got that right. Yep. So we'll use a different color. What I'm calling lecture A3. And so I just want to make sure that we've covered specific key points, vocabulary, rules for drawing CLDs, rules for picking variable names, that we can be gleaned a little bit from some of the reading that we've already done, but it is easy for some of these things to slip through the cracks. So I'm just going to sort of call this causal loop diagrams and model building. Of course, this is SOS 220. And so we've talked about this already, that systems, you know, we can contrast systems with collectives or collections, that is. And systems we can think of, and this is just review, as components whose interdependencies and interactions participate in some larger function. So they're coupled together and they somehow work together. And when you put them together, they do something that they don't do automatically on their own. So it's not like you're taking 5 functions and putting them together, and now I have a group that does 5 things. That's not really a system. You're taking 5 parts that do something else on their own, or possibly nothing, and you put them together, and then they suddenly do something that no one part could do alone. And that's a system. So it's pretty generic definition. I'll just put here, I think we've covered this enough, but I'll just mention here that, there's the components whose interactions allow the sum to be differently functioning than the parts alone. And so it's synergistic. All right, so any questions about that? That's hopefully a concept that made sense from last time, the difference between a system and just a collection of parts. All right, so in order for us to make sense of these systems, we build representations of these systems that let us answer or help us answer, maybe I'll say help us answer, what if questions. And does anybody remember the name that I gave to anything that helps you answer a what if question? A model, right? So this is what we mean by models. And in classes like SOS 212, you'll learn how to build computer-based models, computational models that allow you to generate some of these precise behavior over time plots to show you how a system is predicted to behave over time at a second-by-second time scale. In this class, we're not building quantitative models. We are building, so in SOS 220, we build what we're referred to as qualitative models. Which by qualitative, I mean it captures sort of a family of behaviors rather than sort of a precise thing. So we know that this particular system might grow, this particular system might collapse, this particular system has the opportunity to oscillate, to change over time. This particular system is vulnerable to this threat. This particular system is vulnerable to that threat. These are qualitative. We're not saying that it's vulnerable to exactly this amount of that threat. That would be like a quantitative prediction. So a qualitative prediction, this tells us about kind of the quality of the system as opposed to the precise quantity of how much is needed to get a system to tip into one regime or another. And we capture that, at least starting here, the framework that we have been introduced in Unit A is the causal loop diagram. And that just sort of captures the causal relationships among system, and then I'm going to use this term variable. And then that's not events. So if we think back to that reading, they said one of the things in the event-oriented worldview, we could imagine things that happen, like somebody walks in the door, somebody sits down, class starts. Those would all be events. And we could diagram a sequence of events that, somebody, goes to the door, they sit down, then class starts. And then someone else comes in the door, sits down, and so on and so forth. And that can be a useful description of what has happened in a system, but we are not interested in events. We are interested in the systemic structures that generate those events. And so we are focused not on events, but on this term variables, which are these things that I'm going to define in more detail here, but roughly speaking, these are things that can change over time. So variables, they're called variables because they vary over time. or can change over time, which is why we are particularly interested in things like behavior over time plots, and things that change over time, we refer to them as dynamic variables. And dynamic, the hidden aspect of the word dynamic is that we care that it changes over time, but the difference between dynamic variables and say kinematic variables, there's other sorts of fancy words we can use, is that we also care about the forces that cause those changes. And so when we talk about dynamics, you can say these are the causal forces that drive change over time. So if I say I'm building a model, a dynamical systems model, what I'm saying is I'm going to represent a model to you how different things that change over time cause each other to change over time. And so the interrelationships among how things change over time and how that helps explain why they're changing over time. So some of these things might change on their own, but most of the time they're going to be interrelated. So that when it gets hotter in the room, maybe it changes your ability to take notes. And maybe as people leave the room because they can't take notes anymore, it gets cooler in the room. And so people then start being able to take notes again. So that would be an example of an interaction of these dynamical variables. The number of people in the room, it's a dynamical variable. The temperature of the room is a dynamical variable. The ability to take notes is a dynamical variable. It all interact into a system which has to do with taking notes. So those are the types of things that we're interested in here, and I want to focus today to start with on these variables. What are they? How do we choose them? How do we choose not to choose them? What types of things can they be? What are the rules? So any questions about any of these things so far? What do you mean by dynamics and all that? No, it's a little abstract. Things will get more concrete. Okay. All right, so let's think about these variables. In our system models. All right, so when we build a model of a system, we have different types of variables. And I'm going to use these terms, and you'll find that different texts will use these terms: endogenous, exogenous, and excluded. So let's figure out what that means. And so endogenous, let me write that out a little nicer just because it's a kind of a interesting word. Endogenous variables, their value is determined by other variables in the model, in the system. So value is set, or I'll say determined, by other vars in the model. And I want to contrast that with exogenous. And exogenous vars is that their value is set externally. You could say by the modeler. So as an example, if I talk about this room, I said, there's the temperature in the room. Now, initially I said the temperature affects your ability to take notes, and your ability to take notes affects your decision to stay in the classroom and listen to me. So your ability to take notes is determined by temperature. And your willingness to stay in the classroom is maybe set by your ability to take notes. So ability to take notes and willingness to stay in the classroom are endogenous variables in this model of behavior, of social behavior. The exogenous variable for now is temperature. And so if I had those, so if I were to write this little example, if I said I've got temperature and it affects ability to take notes, and that affects willingness to stay, then I would say here that these two are endogenous, and this is exogenous. And why is that important? Well, if I wanted to run scenarios, I could say, well, what would happen if I taught in a room that was 60 degrees, 65 degrees, 70 degrees? And so I could sort of model different classrooms within different temperature ranges. I wouldn't be saying I know why the temperature is set a particular way. I'd say maybe I assume I have control of the temperature, or if I don't have control of the temperature, I could do scenario planning. I could say, well, what's the worst case temperature I might be able to get in this room? What's the best case temperature I can get in this room? So certain rooms, based on their bounds for temperature, I might have to teach totally differently, because I'm like saying, well, it's that hot, there's just no way that, we're just gonna have to go outside half the time or something like that. Whereas other rooms, if they're really cold, I might have to teach in a different way. But this system would still be at play in all of those rooms. And I refer to this as being exogenous because it's an external parameter that me as a modeler, I have to decide the value in order for me to make quantitative predictions. Now, I mentioned to you that there could be a feedback between the number of people in the room and the temperature. So I could imagine a modified system where I would have the temperature contributes to the ability, and I'll say to take notes. I'm just going to do ... and that temperature is to the willingness to stay. But then that contributes to the number of students in the classroom, and maybe that contributes back to temperature. So now I've closed the loop. So this is a close the loop on temperature. So this up here we can view as open loop. So temperature is an input. And now temp is part of a feedback loop. Now, what I just did here is I turned temperature from an endogenous or from an exogenous variable to an endogenous variable. And so this here, sometimes we refer to as endogenizing an exogenous variable. And I'll just mention here that now all are endogenous. So I went from a very simple model that helps me do scenario planning. And then I can say, well, thinking about it, I actually know that there is a process that it sets temperature in the room, and it has to do with the number of students in it. So if I introduce the number of students into this model, it allows me to create a model that helps temperature be set inside the system, so that I now don't have to come up with what are the possible parameters that I need for this. And so that is what I did, and now to create all these being endogenous. Now, number of students, that is something that I'm going to define, but I mean, I can define it here as what I would refer to as an excluded variable. So we know that all models are wrong, but some are useful. You will always exclude variables. We need simple models to make sense of the world, because we want to test hypotheses about components of the world. Does this really matter to that? Well, maybe this and that and a couple other things are all you need to test whether this matters to that. all the rest of the stuff maybe is irrelevant. It just gets in the way. So if I really am interested in temperature and students' willingness to stay in the classroom, maybe this is all I need in my model. But if I then need to test theories about how temperature changes over the class period, then I need to expand my model, complexify it, add more to it, and then add other variables. So I did not put number of students in my first model, so it was excluded from my model, but I could have, but I decided that I don't want to bother adding in number of students somewhere in here because it's not interesting to me in whatever I'm studying up here. But when I decided to get a process to better explain how temperature changes over the 75 minutes, then I needed to include number of students as another endogenous variable. So that's what I mean by endogenous, exogenous, and excluded. And this process of endogenizing as you go from a simple model to a more complex model where something which previously was an input now becomes sort of the internal guts of your model. And I could have other exogenous variables here, the day of the week or something like that. I just happen to have created a more complex model where everything's endogenous. Yeah. Yes, yeah, I would say, I can put that, I think that's a great definition there. So I can say, then I'll say excluded on next page. And then so an excluded variable is a variable that may play a role in the larger system, but is excluded from the model to better focus on other specific interactions. And so, again, I'll just put the quote here, all models are wrong, but some are useful. And this again was a quote from statistician George Box, GEP Box. And then, creating useful models sometimes means simplifying models to exclude, I'll say, less relevant parts. It's kind of like with a microscope. I can look at a cell culture or something with my naked eye, and I only see certain things. And then I look at the microscope and I can focus at different depths, or I can use different magnification levels. And that will expose other parts of that cell culture. But at no point do I ever see everything all at once. So I have to choose what I'm interested in at that time, which will mean excluding some interest. And so we have to figure out how best to exclude things when we're coming up with models. And we'll comment more about that in a second. So any questions about this? So this is pretty clear so far that when we build models or causal loop diagrams, the things that have inputs basically, so if it's got an input coming into it, it's endogenous. If it only has an output, then it is exogenous. Sorry, well, this here has that, so I guess I should get rid of that guy. So maybe I'll highlight this. I'll say that the endogenous ones, they're the ones that have an input. The exogenous ones, they only have an output. The endogenous ones can have outputs, but the exogenous ones only have outputs. So then this guy. And then the excluded ones are ones that are probably important to the real world system, but we've chosen to exclude them because our focus for this particular research question, we don't think that it's useful to add that extra complexity and that it's only going to get in the way. Okay. All right, so sometimes we refer to the exogenous variables as marking the boundary of our system, so of our model. So I could imagine, saying that if I picture a model, I've got my endogenous being sort of on the inside, and then I've got my exogenous is the sort of interface to the rest of the world. And then my excluded are all around it. So I've got my endogenous here, my exogenous is the boundary, and then my excluded are just not even in the CLD. And so sometimes we refer to the exogenous as sort of the boundary of the model. Sort of one visualization. The stuff completely determined internally, the stuff on the outside that allows, it's permeable, it allows information in from the outside world, and then the stuff that we're not even considering. Okay. All right, so a question that we might have is, how do we decide what to exclude? So also that's the question I'll start on the next page. How to decide what to exclude. And I should also say that delays fall into this sort of as well. Like we'd say, well, how big is a delay? Well, if I might choose to just exclude delays entirely because I don't think they're important to my phenomena, or I can put them in. So delays are sort of kind of related to this here, like which interaction has a delay and which doesn't. That goes right along with deciding if are we going to exclude it or not. So the question is, how do we decide what to exclude? And so there's not a exact, I can just give you a couple of examples that kind of cut across a wide range of cases. This is probably not an exhaustive list. It's one of these things you sort of build up. It's like kind of like the definition of life. If you look up the definition of life in a biology textbook, they'll give you like 6 or 7 different items, but then you always find counterexamples or exceptions. But by learning kind of those rules, you kind of get like the gist of what you're getting at there. So, one application area is hypothesis testing. So the idea here is I have some hypothesis about how the system works, and that hypothesis necessarily involves a small number of variables. So I have a hypothesis that temperature affects your ability to take notes from me, but not noise, acoustic noise or something like that. So I might not include the noise of the air conditioning system in my model because I want to say if it was only temperature, then what predictions would I make about your behavior? And if you don't behave in that particular way, it allows me to reject the temperature hypothesis and look for other hypotheses. So hypothesis testing here is sort of like we only include the variables necessary to capture the hypothesis that way. Deviations from model predictions indicate hypothesis is flawed. So, if we we're talking about biodiversity or something in a forest, we might have some hypothesis that we need a particular type of diversity, or we need a particular set of organisms. And so, we may not focus on all of different aspects of the ecology of that forest, because we can test that hypothesis with a smaller set. And so, oftentimes, if we're testing a hypothesis, we need to build a model to sort of that assumes the hypothesis is true, and only that hypothesis is true, so that if the model's predictions are wrong, it only speaks to the single hypothesis that we're testing, and doesn't confound one hypothesis with another. So we're trying to avoid, so we exclude in order to avoid confounding hypotheses. Any questions about that? Does that sort of make sense? That if you want to test, yeah. Or you might, so usually, so when we talk about hypotheses, there's technically the statistical hypotheses that you probably hear about, like a stats course where you've got a null hypothesis and your alternative, and there's just two, whatever. Stats hypotheses are sort of, when you get into science, and includes sustainability science, the stats hypotheses are really like, how do we find patterns that are interesting, so they can't be explained by chance? That's really the stats hypothesis. But what I'm talking about as a research hypothesis would be like, I ask a question, like, what determines recycling rate in a city? There are probably 5 or 6 different answers to that. Each answer is a hypothesis. So hypothesis is a plausible answer to a research question. And so we could say, all right, well, let's, does the amount of, does the color of the recycling bin affect compliance rate? Well, under the hypothesis that the color of the bin determines the recycling rate, then I could go and do an experiment, and I could go into different parts of, I don't know, Chandler, and give them different colored recycling bins and study the rate. If the rate doesn't vary with color, then I can reject that one hypothesis and go to the next one down. So it might mean going back to the drawing board and augmenting your hypothesis until you get something that matches, but it might mean just totally throwing that thing away and going to the next one in your list. So a hypothesis is a plausible answer to a research question. And just like in that color example there, if my hypothesis about the color of the recycling bin, I probably need to control for everything else. So the recycling bins all should look the same, except for their color. Because if I also made some recycling bins larger and some smaller and those sorts of things, then now if I find that there is a difference in recycling rate, I won't actually know if it's due to color or the size of the bin. So, so that's what I mean by excluding variation in order to avoid confounding hypotheses. So that's what I mean by hypothesis testing. Any other questions about that? Is one reason to exclude things, or what to choose to include. The other thing, the other big one, is you want to make sure you include limiting, this is a term I'll kind of define here, phenomena or variables. So what I mean by that is, like, for example, consider oxygen level in a room. Probably do not include in model of ASU, but include in model of Mars community, or maybe a or underwater community. So if I want to imagine, like, what drives people to move around different buildings at ASU, oxygen is not limiting. Oxygen's important. It's important to all of your physiology right now. I could build a causal loop diagram of any process, any social process here at ASU, and include oxygen in it. I could, but it would be dumb to do, because the amount of oxygen that's available to all of us across ASU is not limited. It will never be a factor. It will never affect things. Now, if I'm modeling instead how people move around in a new installation on the first base on Mars, well, then I really have to start worrying about, well, the oxygen levels, the carbon dioxide levels. This is going to start making people feel loopy if the carbon dioxide gets a little high. And that is going to need to respond. There might need to be feedbacks that people need to then move based on those things. And so suddenly oxygen and the lack of carbon dioxide and those sorts of things become limiting factors. They become drivers. The availability of them helps drive the system behavior. So if you're throwing in variables, which you know from your basic knowledge of human physiology technically are operating there, you need to ask yourself, though, is there any scenario where these variables would actually vary to a significant level that it would change things? Like, you know, in all ASU classrooms, we can pretty much assume a certain oxygen concentration or higher, and it doesn't really matter once things are above that. And so we probably don't need that. So that's what I mean by limiting. So we can exclude things that are not limiting. So I could say include maybe only limiting phenomena or variables. Any questions about that? What I mean by limiting? Likewise, nitrogen in the soil or something like that. It might be that there's plenty of nitrogen in certain forests in the soil, and so it's not limiting. But what is limiting is the availability, the amount of sunlight. So everything I know about plant physiology says that nutrients in the soil, as well as the sun, are both important for plant physiology. So if I really want to really model every single thing that happens in every single plant, I need to account for nitrogen and sunlight and other things. But if I'm trying to imagine, like, what describes the canopy dynamics of one canopy versus another, then if I go into a region with really poor nitrogen content, those trees are going to act very differently than regions with high nitrogen content. And so the nitrogen content becomes super important, and it might totally change patterns in a forest with poor nitrogen soil. You get totally different adaptations and so on. But if the limiting nutrient or the limiting thing in another forest is something other than nitrogen, the adaptations we expect to see are going to be for that thing that's limiting. Maybe it's carbon, maybe it's phosphorus, maybe it's something else totally entirely different. So, so we only include the things that are limiting. Things that are just we get for free in excess, you probably don't need to include in your model. Your model will probably be better if you exclude them. Questions on that? Okay, and I guess sort of the big thing here is you have to kind of ask the question, would model predictions be qualitatively different. This is where we're interested in qualitative models. If I remove the variable. If not, then consider excluding. And this goes back to thinking about a kitchen as just a collection of items. Like if I'm making, I don't know, a cake or something like that, maybe I don't need the sharpest knives in that process. So maybe the number of knives I have in the kitchen is not a variable that needs to be included inside my causal loop diagram, because it's not limiting. And if I took the knives away, the process of making the cake would end up being identical. And so those are the types of things, is like, we don't just want to throw in, we're not trying to diagram all of the possible things that could remotely be involved. We're trying to diagram the kind of salient features, the key features of the system. And we want minimal models, because those minimal models help us really extract the key points, the key feedbacks that are driving most of the system behavior. Our goal is to explain 80% of variation in the system, Gesundheit, even if that means leaving 20% on the table, because to get that last 20% of variation, it may require a far more complicated model that we lose all insight, all generalizable insight from. All right, so any questions about what to exclude? It's kind of like all I want to say to that, but I will, I'll make the sort of note again that this applies to delays as well. And I'll make another comment about delays a little later if we get to it. Okay. All right, so we've got excluded, exogenous, and endogenous. We've got endogenizing variables, we covered that. And sort of just generally model complexification. Start with simple models, go to more complex models in order to sort of make your models more and more realistic, but usually start simple and then build out as opposed to the other way. Okay, so I guess I can give sort of maybe a sustainability example of that. So example, fisheries management, which is a sort of a classic conceptual model for a renewable natural resource. And I should say that in renewable natural resources, usually rates are limiting. So since renewable, rate is limiting. But in a non-renewable natural resource, the absolute amount of the resource is limiting. So somewhere in my model for fisheries management for a renewable resource, because fish are renewable, I probably need to tip my hat somewhere in the model to the rate of regeneration and the rate of depletion, because it's the rate which affects whether the fishery is sustainable. But if I'm doing a model of oil excavation, it's the actual amount of oil that probably needs to show up, not necessarily the extraction rate of that oil. Maybe the extraction rate's important as well, but that's just trying to draw a highlight to these things, this idea of limits and limiting, what's limiting. And so if we think about a simple model of my fishery, then let's say that things that I definitely want to include in this model might be fish population and regeneration rates. And that's what I'm going to bundle in as my endogenous variables. But then at the boundary of the system is my exogenous variables. So I'm interested in knowing, how does harvest rate affect the sustainability of this fishery? Well, I don't know how harvest rate is set in nature. So I'm going to make it an exogenous variable so I can then sort of imagine what would happen at a low harvest rate, what would happen at a high harvest rate, and so on. So I then will create a exogenous variable called harvest rate. Sorry, not highlighter. And maybe one other thing that I think is important is the carrying capacity. Everybody know what carrying capacity is from like SOS 101? So it's like the maximum amount of fish that can be sustained in a fishery. So maybe the carrying capacity is also an important thing. So these would be two examples sitting on the boundary of my model of my exogenous variables. And so that helps me then experiment. So I can say, if I increase the carrying capacity of my hypothetical fishery, what happens? If I increase the harvest rate of my hypothetical fishery, what happens? And then I can sort of, the fish will just naturally inside my model in the endogenous will just bounce back from however I change these parameters here. But then the things I'm excluding might be things like the number of boats in the fishery or a harvest quota. So like number of boats in fishery and maybe a harvest quota. So this is a policy. So yeah, I'll just maybe put that here, policy. And so these are examples of excluded variables, at least for now. And if I could build a model where these could be the exogenous variables that determine the harvest rate. Because if I know the number of boats in the fishery, and I know that all the boats have a particular quota that they can't go any higher than, then I might be able to use these two pieces of information to come up with a harvest rate. So then I could say, now I can experiment with the number of boats in the fishery. So at what point do I get too many boats in the fishery for the fishery to be sustainable? But here I'm sort of saying, I don't know how harvest rate is set, but I'm going to experiment with harvest rate. So I can complexify the model by adding in these things to determine harvest rate, and that would endogenize harvest rate. But maybe carrying capacity would still be an exogenous variable. It's just something I set. For this fishery, it's this carrying capacity. For that other fishery, it's another carrying capacity. So any questions about that? I do want to list that there are some synonyms for exogenous variables. Sometimes we're going to refer to them as slow variables. Or parameters. But basically, these all mean roughly the same thing. Okay. So questions about that, clarifications. All right, so that's kind of our categories of what are the types of variables, but how do we know like what a variable is, like at a more fundamental level? How do I know that harvest rate, fish population, regeneration rate, how do I know that these are all good variable names? What makes those variables and other words totally off limits as variables? And so, it's like, what's in a name, what's in a variable? So what is a legal variable? And so there just are kind of a couple of rules that to tend to sort of have withstood the test of time here. And so all variables are going to be nouns or noun phrases. So some examples, ice, like sea ice, or sea ice, I guess. That's good. But ice melts is bad. So I guess I could cross that out, something like that. So, and that's because this sort of as a verb or action. It's not a noun phrase. So as I'll say in a minute here, I want the variables to sort of be measurable and have quantity. And a verb doesn't have quantity, but a noun does. I can say there is so much ice, there is so much sea ice, there is so much ocean reflectiveness. Those are things that I can measure. They're noun phrases. But other kind of examples here, good examples here, like water level. That's another fine one. Mature fish. So I can talk about the number of fish, or I can subdivide that and say, well, there's juvenile fish and there's mature fish. The mature fish are the only ones reproducing. The juvenile fish will reproduce, but you have to wait for them to become the mature fish. So we have to model that demographic process too, in our model. And notice that in some of these cases, we often imply a number of or amount of. So I can't really say amount of ice melts. I could say amount of melted ice, but I probably would just say amount of water. So I can say I can provide adjectives, but I can't be an action. All right, so going along with that, the other rule here is that I need these variables to have a sense of direction. Another way to say that is they need to be potentially measurable or sortable. And so some examples of that, I could say happiness, for example. That is a totally reasonable variable because it is, you could take a person's happiness and you could say they are less happy today than they were yesterday. That implies that there is some way, I don't know, I'd have to talk to Scott Cloutier or somebody else who studies happiness, and I could actually then have them say, well, how would you survey someone to get an estimate of their amount of happiness? But in principle, I could do that. And then that could then sort me over time or me versus you and those sorts of things. So it is a measurable quantity and it has a sense of direction. You can be more happy or less happy. So you can put it on an axis, you can put it on a scale. That's what sort of one example there. Or temperature, that's another one. Maybe is a little easier. It's easy to imagine rooms of different temperature. There's hotter temperatures, there's cooler temperatures. Not say attitude. So this is a check, this is a check, this is not. So attitude, you can say someone has a good attitude or a bad attitude, but it's not sort of a numerical thing. It's like an either or. They're either have a good attitude or a bad attitude. I could say morale, maybe, and because then you can kind of sort morale or whatever. I can say they're positive or something like that, but attitude by itself is ambiguous. If you just say attitude without extra details, you don't know what it means. And so just provide the extra details. Another example might be status. So so status is something that like you have to be more detailed to sort of say, well, what am I, like, you can say, what is your status? And say, well, I'm single. You know, what is your status? Well, I'm married. Well, where does that go? Single versus married, you know, on the axis. Like, it doesn't have a quantity. It's not measurable. It's just categorical. So it needs to be orderable, I guess. So sortable, or if you prefer, we could say orderable. So there's got to be something numerical about it. And then the last thing is more of a preference. Some textbooks are really into this, some not so much. I mention it because I think it's a good preference, but it's not to me a hard and fast rule. But we prefer the normal direction of the variable is positive. Now, what the heck do I mean by that? An example of that would be like profits would be good, but not losses. So profits and losses both meet these rules, but we like to sort of by default, whenever possible, make the variables kind of positive so that any sort of negative, like we'd like to show in our causal loop diagram, that if you make some change in the system, it will decrease profits. We'd rather decrease profits than increase losses. To me, again, this is more of a preference, but it does sometimes make the logic clearer if you stick with this preference. So, but it's not always possible. Sometimes this isn't as clean to implement, as we just may not have a concept for the positive side of it. All right, any questions about these sort of rules? Pretty clear. All right, so just emphasize here, these are rules for naming CLD variables. Yeah. Yeah, well, so and when we start, if you're imagining, I was drawing like a CLD that had, and I haven't really got into, you know, I mean, we've talked a little bit about CLDs, and so I'm going to talk about links next. But if I were to draw something that said like, you know, with more advertising, then I could either put profits here. And so I could say, well, with more advertising, hopefully I make more profits. And with more profits, I can have more advertising, and those two things will grow. I could have drawn the same thing, but I could say with more advertising, the losses decline. And with losses, I'd have to say with more losses, advertising declines. With more advertising, losses decline. This is a positive feedback loop, which we'll remind ourselves about here, the same as this. These are identical, but most of the time this is just awkward because, you know, I've kind of like, rather than inverting this twice in a positive growth loop, it's better to just sort of take the positive thing instead. Okay. So I'll just maybe put a note here that this one is more intuitive. And that's why we have this preference. Any other questions? All right. Home stretch here. So, so what is a causal link? So causal loop diagram is not only variables, it's also the causal links. And so I could draw a causal link between two variables, like A goes to B, and this might be positive, or I could do X goes to Y, and this might be negative. I could also, instead of writing positive, I could do same. Instead of negative, I could do opposite. And so a key thing here is this represents a causal relationship, not merely correlational. So there are sort of the classic logical fallacies. If you've taken a philosophy class, you might be familiar with post hoc, ergo propter hoc, or cum hoc, ergo propter hoc. So these are fallacies. And this basically means happens after, therefore happens because. And this one's the same thing, but this is happens with, therefore. So I bring those up because there are a bunch of phenomena in a system where two things will happen to be correlated to each other, but they often have a common cause. So, as sort of an example, if, they could say like, well, sunburn is related to, sunburn happens to be correlated with ice cream sales. And well, maybe I'll flip that because maybe there is some weird, there might be some weird thing when you get a sunburn, you actually want more ice cream. Like that might actually be a causal relationship, but this is probably not a causal relationship. It may be that in the summer, ice cream sales go up and sunburn goes up. But it would be wrong to assume that ice cream sales cause the sunburn to go up. This is purely correlational. So, this here, I'd say is wrong because this is correlational. But if I instead had something that was like temperature, well, as temperature goes up, so do ice cream sales. And as temperature goes up, so does sunburn. So it turns out that these two variables are not directly related to each other. They just had a common cause. So this here is causal. So the key thing we're trying to get here is that this is representing causal theories, causal relationships between variables. And so how do we interpret these pluses and minuses? So what we can say is imagine if you made the system's running along fine, and you made a change to A or a change to X, and then you want to analyze the resulting change to the effects B or Y relative to whatever they were doing beforehand. Then the plus and the minus, or the S and the O, which are just synonyms for that, represent the relationship, the directional relationship between the change in the cause and the change in the effect after the perturbation. So the link here is represents directional relationship between small change in cause and resulting change in effect relative to no change baseline. So the system's humming along and the current enrollment rate at the university is B. You make a change to advertising A, and then you see how the enrollment rate changes relative to what it was. And so it might be that you increase the advertising and the enrollment rate goes up. And that would be this A to B thing here, where an increase in A caused an increase in B. Or you could decrease advertising and the enrollment goes down. Decrease in A causes a decrease in B. That would be the A to B. X to Y here would be the opposite, where increase in advertising causes decrease in enrollment for some reason, and vice versa. Decrease in X might cause an increase in Y. That's causal links. The other trick here is that we have to evaluate these one at a time. So if I have like A, B, C, X, and Y, and everybody's got links going into C, it may be that A also has links going into B. So it might be that A going into B is a plus, X going into C is a plus, Y going into C is a minus, B going to C is a minus. And I am trying to figure out, this sign here. I have to evaluate direction, pretending changes in A are not reflected in variables other than C. So what I'm saying here is I might know that if I increase A, B is going to increase. And I already know that if I increase B, C is going to decrease. So there is a causal pathway from A to C this way. But if I'm focused on just this line, I have to pretend, what if B didn't exist? Or what if there was a way to increase A without B noticing? That is what I'm saying. What is the effect of A by itself on C? That's what this here is. So, so you have to try to put yourself, it's in math or in calculus, you refer to as a partial derivative. So it's like the sign of the partial derivative of C with respect to A. You have to somehow imagine that the rest of the variables are held constant, and the only thing that changes is A to evaluate that thing there, C. Any questions on that? Okay. So I don't really think want to go, I think, much farther here. The only other comments I really had were naming the feedback loops, which we've already talked about. So maybe at the start of our next session, before the reading, I'll just finish this up and remind ourselves about feedback loop polarities. So for today, let's do the attendance slide here. So the question that I have for you is, how about what is the type of variable that is solely determined by other variables in the system? So it is, and it's an input to the system. It's not on the boundary of the system. It's firmly inside the system. What is the name of that type of variable? So the question is, what is the name of the variable, the type of variable that is firmly inside a system? What is the name of the type of a variable that is only determined by other variables in the system? It is not determined by the modeler themselves. So it's driven entirely by other variables in the system. And as a hint, there are 3 types of variables. We kind of started things off with them. And that's all I got for you. Remember, there's a reading on system traps for Thursday, and we'll wrap up feedback loops and start that reading for Thursday, reading discussion for Thursday. And if it's helpful, my own personal lecture notes for this lecture, I posted with this lecture online. If you want to use that as sort of a reference, I tried to write them out in more longhand than I normally do, just to give you a little bit of a reference. Yep. Have a good day.